Ever feel like you're just drowning in information? Facing this huge wave of data, but what you really need are just those few clear insights.
Oh, absolutely. Like trying to find that needle in a haystack. But the haystack is, well, the entire internet.
Exactly. And it feels like the sheer amount of data just keeps growing, making it almost impossible to keep up sometimes.
Which is why tools that help us make sense of it all quickly are becoming so vital. It's not just nice to have, it's, well, essential.
Totally agree. And that brings us neatly to our topic today, LlamaIndex. You can think of it as like a really smart research assistant.
Right. Its whole purpose is to take all that raw stuff, documents, web pages, data from APIs, you name it, and help you extract actual knowledge from it.
So our deep dive today is all about unpacking that. We want to understand the core pieces LlamaIndex uses, how it, actually works under the hood.
Yeah, we'll look at how it ingests data, how it structures that data, and then, crucially, how you can query it to get useful answers back.
And the sources it can handle are pretty broad, right? We're talking local files, stuff from online services.
Oh, yeah. Local files, live data, via APIs, even scraped web content. It's designed to be flexible.
Okay, cool. So let's get into it. Where does the process start? How does data first get into LlamaIndex?
It all begins with what LlamaIndex calls data connectors. These are really the entry point.
Data connectors. Okay, so they're like the gatekeepers bringing data from wherever it lives into the LlamaIndex system.
Precisely. They bridge that gap. And there are different types depending on the source. The most straightforward are probably the file connectors.
Right, makes sense. For pulling in things like PDFs or Word docs sitting on my hard drive.
Exactly. All those local files we collect. Very direct.
But what about data that isn't local, like information from a live service online?
Good question. That's where API connectors come in. They let LlamaIndex talk to external web services through their application programming interfaces, their APIs.
Okay. I think our source mentioned an example, like fetching weather data.
Yes, exactly. It showed using Python's requests library, which is super common for this kind of thing to hit a specific URL.
Something like that, open weather map URL, yeah.
Yeah.
And it mentioned using timeout 10. Why is that important?
Well, you don't want your program to just wait forever if the weather service is slow or down, right?
Yeah.
Timeout gives it 10 seconds, and if there's no response, it moves on. It adds robustness.
Got it. And there was also response.raise for status.
Yeah.
That sounds like error checking.
It is. It automatically checks if the request was successful. If the API returns an error, like page not found or access denied, this line will catch it immediately.
Smart. So it handles API problems up front, and then the data comes back in JSON format.
Usually, yeah. JSON is very common for APIs. The code then uses response.json to parse that JSON data into a Python structure that's easier to work with.
And then LlamaIndex takes over.
Right. LlamaIndex provides an AppData connector class. You use its load data method, feeding it the data you just fetched and parsed.
And I noticed they wrap the whole thing in a try.except block.
Yeah.
More error inherent.
Yep. Network connections can be flaky. APIs can go down. That try dot, except make sure that if something goes wrong during the fetch or the processing, the program doesn't just crash. It can handle the error gracefully. Reliability is key.
It really seems built for dealing with real-world messiness. Okay, so files, APIs. What about just grabbing info from a regular website? The source mentioned ethical web scraping.
Right, web scraping. That's extracting data directly from website HTML. The ethical part is crucial, though.
What do you mean?
Meaning you need to be respectful of the website owner. The most basic step is checking the site's robots.txt file. It tells automated tools like scrapers which parts of the site they're allowed or not allowed to access.
Ah, okay, so play by their rules. The example code didn't show checking robots.txt, but you're saying that's a fundamental principle.
Absolutely. It's step one for responsible scraping. The example did show using requests again, but this time with a headers dictionary.
Yeah, user agent. Mozilla 5.0. What's that about?
It basically tells the website, hey, I'm making this request using code that looks like a standard web browser. Some sites might block requests that don't have a plausible user agent. It's generally seen as, well, better manners.
Gotcha. Be a good digital neighbor. Then they use something called Beautiful Soup.
Ah, Beautiful Soup. Yeah, it's a fantastic Python library for parsing HTML and XML. When you get the raw HTML back from a website, Beautiful Soup turns it into a structured object that's easy to navigate.
So it helps you make sense of the web page's code.
Exactly. The example showed Beautiful Soup response.text HTML.parser that takes the raw HTML text and parses it. Then soup.getText is used to just pull out the actual human-readable text from the page, stripping out all the HTML tags.
Okay. Okay, so it cleans it up nicely. And similar to the API connector, there's a specific web data connector in LlamaIndex.
Correct. And a web connector.load data method, again, typically wrapped in try dot, except for robustness against network issues or problems parsing the page.
It's a recurring theme. Get the data, but do it safely and reliably. The source also mentioned a figure 1 data connector diagram. I guess that visually sums up these different ways data can flow in.
Yeah, it helps picture how LlamaIndex acts as the central point, pulling information from files, APIs, websites, all sorts of places using these connectors.
Okay, great. So the connectors get the data into LlamaIndex. But once it's in, what happens then? How is it organized?
That's the next crucial step, indexing. LlamaIndex uses various data structures, which it calls indexes, to organize the information efficiently for later retrieval.
Indexes. Like the index in the back of a book, but more sophisticated.
Kind of, yeah. They structure the data so you can find what you need quickly. And LlamaIndex offers several types, each suited for different needs. The simplest one mentioned is the ListIndex.
ListIndex. Sounds pretty basic. Just list the documents or data chunks one after another.
Essentially, yes. It maintains the data in a sequential list. Simple to understand, good for maybe iterating through everything, but not the best for complex searches.
Right. Probably gets slow with lots of data. What else is there?
A really important one is the VectorStoreIndex. This is where things get, well, quite powerful. It uses machine learning concepts.
VectorStoreIndex. Vectors. Like in math. What's the idea here?
Sort of. It involves converting your text data into numerical representations vectors that capture the semantic meaning of the text.
Semantic meaning. So not just keywords, but what the text is actually about.
Exactly. It understands that dogs and puppies are related, or that economic downturn and recession are similar concepts, even though the words are different. The index then stores these vectors.
And how does that help with searching?
It allows for similarity searches. When you ask a question, LlamaIndex converts your query into a vector too, and then looks for data chunks whose vectors are mathematically closest or most similar in meaning.
Wow, okay. That sounds much smarter than just matching keywords. Our source had a Python snippet for this.
Yeah, it showed creating one .python from LlamaIndex.core import, VectorStoreIndex, documents, doc1 content, doc2 content, doc3 content, VectorIndex, VectorStoreIndex.from documents,
Right.
print, VectorStoreIndex created with, then documents.
And it mentioned chunk size 512. What's that doing?
Chunk size. Large language models, which often power the vector creation and querying, have limits on how much text they can process at once, often measured in tokens. So chunk size breaks your documents down into smaller, manageable pieces or chunks before they're converted into vectors. 512 tokens is a common chunk size.
Okay, so it makes large documents usable by the underlying models. What other index types are there besides list and vector store?
Well, there's the tree index. As the name suggests, it organizes data hierarchically, like a tree structure.
So good for data that already has a kind of parent-child relationship, like sections and subsections in a long report.
Exactly that kind of scenario.
Yeah.
It can be really effective for summarizing information at different levels or navigating structured content.
Makes sense. And then a keyword table index? That sounds more traditional.
It is. It basically creates a map or table linking specific keywords to the documents or data chunks where they appear. Very fast and efficient if you know the exact terms you're looking for.
So less about meaning, more about specific word occurrences.
Precisely. And then perhaps the most flexible one is the ComposableIndex.
Composable. Sounds like you can build with it, like Lego bricks.
That's a great analogy. It allows you to combine multiple different indexes together.
Oh, interesting. Why would you do that?
Well, imagine you have data that benefits from both semantic understanding and specific keyword lookups. You could create a vector store index and a keyword table index separately, and then combine them into a single composable index.
So you get the best of both worlds when you search.
Exactly. Or you could combine a tree index for structure with a vector store index for semantic search within the nodes. It offers a lot of power in how you structure and access your information.
That sounds really powerful. The example showed combining a tree and keyword index, right?
Yep, something like this. Python. From LlamaIndex.core, import tree index, keyword table index, composable index, tree index from documents, section 1, section 2, section 3, a keyword index equals keyword table index from documents, keyword A, keyword B, composable index, imposable index, keyword index, print composable index created with one composable index indexes, sub-indexes.
Very cool. And again, the source mentioned a figure 2. index type diagram to
Yeah.
help visualize these different organizational structures.
Right. It helps clarify how you can tailor the organization to your specific data and needs.
Okay, so connectors bring data in, indexes organize it.
Mm-hmm.
How do we actually get answers out? That must be the next step.
Absolutely. Once your data is neatly indexed, you need a way to interact with it, to ask questions. That's the job of the query engines.
Query engines, the part that does the actual searching and thinking based on the index.
Precisely. They take your query, interact with the specified index or indexes, and retrieve or synthesize an answer.
And just like indexes, I bet there are different types of query engines.
You bet. The source mentions the simple index query engine first. Sounds like the most basic option.
Simple.
Yeah.
So maybe it just does a straightforward lookup, perhaps best paired with a list index or keyword table index.
That's likely the idea, yes. A direct query mechanism without too many bells and whistles.
Okay. What about querying those fancy vector store indexes?
For that, there's the VectorStore query engine. This engine is specifically designed to leverage the power of the vector embeddings we talked about.
So it's the engine that understands semantic similarity and finds conceptually related information.
Exactly. It takes your query, converts it to a vector, and uses the vector store index to find the most relevant data chunks based on meaning, not just keyword matching. It gives you much more context-aware results.
That seems like the key for asking more natural, nuanced questions. The source also mentioned advanced query engines. What's the deal there?
These often take a hybrid approach. They might combine the semantic search power of vectors with keyword lookups for precision, or perhaps use more sophisticated strategies for synthesizing answers from multiple sources. It's about getting more comprehensive or refined results.
Combining techniques again. Makes sense. I see a code example here using the simple index query engine, interestingly, even with a vector store index.
Yes, look, Python from LlamaIndex.core import VectorStoreIndex, simple index query index, VectorStoreIndex from documents, chunk size 512.
Query engine,
This
simple
sounds
index
good.
query engine. Query engine, not curry. Summarize the content of the document.
Exception is print, error during query execution.
So you can use a simpler engine on a more complex index, though maybe you wouldn't get the full semantic benefit. And notice the try.odd except again for handling errors during the query itself.
Always good practice. And the example query, summarize the content of the document, is a classic use case asking the system to process and synthesize information. Right. And I imagine figure 3, query engine flowchart, helps visualize this process of asking a question and getting an answer back via the engine and index.
Yeah, mapping out that flow.
Okay, so the query engine finds or generates the answer, but how does that answer get presented back to me, the user? Is it just raw text?
Good point. That's the final piece. Output modules. They handle the presentation of the final result.
Output modules, so they format the answer.
Exactly. They take what the query engine produces and prepare it for consumption. The source mentions simple response synthesizers.
What would they do? Just clean it up?
Pretty much. They might refine the language, ensure coherence if the answer came from multiple pieces of text, and generally make it more readable and concise, polishing the final output.
Like a final editing pass. And it also mentioned custom formatters.
Yes. This is important if you're integrating LlamaIndex into a larger application. Maybe you don't just want text. Maybe you need the answer formatted as JSON, or put into a specific XML structure, or displayed in a table. Custom formatters let you define exactly how the output should look.
So you can tailor the output precisely for wherever it needs to go next. Super flexible.
It really ties the whole process together. It's not just about finding information, but delivering it in the most useful format.
Okay, this has been super helpful. So just to recap the whole flow.
Yeah, let's tie it together. You start with data connectors to bring in your raw data from files, APIs, websites, wherever.
Then indexes like list, vector store, tree, keyword, or even composable ones organize that data efficiently based on your needs.
Next, query engine simple, vector store, or more advanced ones, take your questions and use the indexes to find or generate relevant answers.
And finally, output modules, including synthesizers and custom formatters, present those answers back to you in a clear and usable way.
Exactly. Those 4 core components work in concert to turn that initial data overload into actionable knowledge.
It really lays out a clear pathway from messy data to actual insights. It's quite an elegant system when you break it down like that.
It is, and understanding these building blocks really opens up the potential for using LlamaIndex effectively.
So, for everyone listening, maybe think about your own data challenges. Where does your information live? What kind of questions do you wish you could ask it?
Yeah, consider how these components connecting, indexing, querying, formatting could be applied in your context. This deep dive gives you that foundational understanding.
Hopefully it's a good starting point for exploring LlamaIndex further, maybe looking into specific use cases or trying out some of these components yourself.
Definitely. There's a lot more depth to each of these areas, but knowing the core concepts is the first step to really harnessing the power LlamaIndex offers for unlocking the value hidden in your data.